Good morning, everybody. Today we have a very special guest, which is Errichto, or Camille.
Good morning, everybody. I can tell you that David is lying to you, and it's not morning for him. It's very late evening.
It is very late. Hopefully in like 36 minutes, though, it will be officially morning, though, so we'll see. Anyway, this is one of at least four, hopefully four for now, episodes of this new series, which we'll call Algo Talk or something else. Two of the episodes will be on my channel, but also definitely check out Errichto's channel on YouTube, and he'll have the other two episodes. And we're going to be doing like the similar style, but with two different versions. So in this episode, we're going to go over a problem that I know the solution to, and Errichto kind of knows the solution, but he's more new to it, so it's going to be kind of me explaining it with him making sure that I don't miss any basic pieces. And then for some of the other episodes, we'll kind of do the opposite thing. So he'll know the problem, and then he'll explain it to me, and I'll try and solve it in front of him. So today we have a problem from IOI, and I think the original problem is called connecting points. But if you're going to call it that, how could you not call it connect the dots, right? So basically...
Isn't it joining points?
Oh, joining points, that's it. Connect the dots is a fantastic name, though. So the idea behind the problem is we'll start with a simpler version first, and then after we'll go toward the more general version. So basically, you have several points. Some are red, some are blue. And they're located in some square, where you have this really nice constraint that no 3 points are collinear.
That's always a very nice constraint for participants, but very annoying one for organizers, because it's hard to create tests where no 3 points are collinear.
For sure. In this case, n is less than or equal to 10 to the 5th, but we won't worry about that too much in the beginning. We'll more get to the runtime at the very end. So basically, just like, let's assume n is something small. You're just trying to get as many points as you can on the IOI style. So now, the goal of the problem is you want to draw some lines, either blue lines or red lines. Your blue lines will only connect these blue points. Maybe you do something like this. And then your red lines will connect the red points. Perhaps something like this. However, you want to do it with an additional restriction, which is you don't want any of the lines to cross. So in this case, we have a blue line that crosses a red line, which means this way of matching them isn't actually valid. So instead, we could, there is a valid way of matching them, which would be something like this. And this is possible. In the problem, it's really nice because they guarantee that there's always some way of doing this. So you just have to find what the solution is, and preferably do it in some reasonable runtime.
Do you remember if the problem said it can be proved that it can be done, or tests guarantee that? Do you remember?
I think the problem said we can prove there's always a solution.
Okay.
But it is the case that you can prove it.
I wondered if they already said that, or you needed to come up with that observation yourself.
They could have said it's guaranteed, right? And then you never know. That's kind of the classic.
The classic, yes.
So I guess when I first saw it, the first thing I kind of thought about was maybe doing some sort of like spiral idea. But I think maybe, Camille, it might be interesting if you like talk about some ideas that you might have in trying to solve it, like your first impressions of the problem, where you might start thinking.
You remember that those are not correct ideas, but my approaches for sure involved some sweep line and convex hooks. One idea is let's go from top to bottom with a sweep line, horizontal sweep line, and let's try to connect points in this order. We know something about points so far. First we have those two red points. It doesn't hurt to connect them. Then for any new red point, I can maybe decide something about that. But what would I do with blue points? I think the main issue is if I don't know the future, then I don't know how this blue point in the top is connected, right? I don't know if there is line like tilted to the left or to the right, like this, or like to the right. So how do I connect anything? How do I now draw any red segment?
Sure, yeah.
The only good thing about this is that if there were only red colors, red points, then this would work. If you're given a bunch of points and you need to connect them into a tree, such that no two segments intersect, then it is fine to go from left to right and always connect point with, for example, the last point, exactly in this way. But doing that for one color might already make it impossible to handle the second color.
Sure, yeah, for sure. So let's just elaborate a little bit on why it might be impossible without looking into the future at all. So, because I think this is kind of like an interesting approach that a lot of people might go down. But it turns out if you don't look into the future, you struggle quite a bit. The reason is we have this blue point here, right? We might want to connect it here. We might want to connect it here. We don't really know what we're going to end up doing. But if we draw this red line here, we might make it impossible to connect this point, this blue point on the top, to either of the bottom corners, and also to any of the other blue points.
It might be. It might happen.
And then the same thing might happen if we pick this other edge here.
And the drawing might be much more complicated. What if we have really a bunch of points? And if there will be like kind of a row of red points, it's very likely that we need to kind of decide what bunch of points on the left is connected with the top left point, which of them are connected with top right point, or maybe we need to do something completely different. They should be connected with something at the bottom, and there will be a big drawing of a snail or a spiral.
Yeah, the spiral examples are also pretty interesting because there aren't really that many ways of doing them. And like most ideas that you have that are like convex hulley tend to get broken by the spiral. Also because the spiral like is particularly tricky because pretty much any algorithm that I was able to come up with that solves this spiral here will break if you make the spiral going in the other direction. So in this case, lots of sweep line algorithms will wind up like cutting part of it off, and any algorithm that like looks at it like this, in this sort of direction, it'll kind of fail if you go in the other direction. The other thing is, it might get even more tricky because initially it's possible you spiral like this, then after a certain point you start spiraling the other way.
I just wanted to say that if you try both options, still maybe in one drawing, in one test, there will be both ways.
And like you can put lots of points here, so pretty much this is like pretty much the only reasonable answer, and it gets very, very difficult. So instead, let's maybe just like take a pause from this sort of greedy approach, and we'll try something slightly different with kind of just like a very helpful observation from the solution. So the idea that the solution uses for this problem is kind of a divide and conquer approach. And you kind of just have to be really, really smart in order to come up with it, which is interesting, but maybe makes it for like a tricky problem because it's hard to say, well, like I should have seen this, because if you don't see it, like if you haven't seen something like it before and you don't just figure it out on the spot, it's hard to come up with something you should have done better.
When we were choosing a problem, I said that it's a bit one-off problem. The idea, the solution from here isn't really that useful in other problems. It's not a good technique to know. Just a nice problem with interesting solution, but that's it. Very unusual one.
For sure, yeah. But I do think the solution is quite cool, how you can think about solving it. And then once you see it, it seems like, oh, that was really easy. I should have seen that earlier. So here's kind of the general idea. Instead of thinking about this as like two very complicated lines, we're going to imagine splitting this graph up like this. So if we draw this line, now what we have is two triangles, one like this, and then one like this. And we know, because there are no 3 collinear points, we don't have any points on this line, either red or blue points. So the line is completely separate, which means we now have a bunch of red points in this triangle here. Possibly some blue ones as well. And then same thing in this triangle. So now, the problem we want to solve is, let's see if we can get like a smaller version of this problem, where we still have one line that's one color, followed by a corner that's the opposite color. So in this left case, the line is blue, the corner is red. We want to see if we can divide this into a smaller version of the problem that has fewer points, where we have the base being one color and then the other opposite corner being the other. So I guess, Camille, do you have any ideas on how we might handle this? What we might do?
We might recursively take some point inside. And this is idea which comes from triangulation of a set of points. Triangulation of a polygon, I think. This is the first step of, how is it called? Voronoi diagram. Right? We can take any point inside and connect it with the 3 vertices of a triangle.
So what if we pick maybe this point right here?
This is not a good idea, because then we have a blue triangle, and that's different style than what we start with, where there are 3 blue vertices. So we need to take red point for sure.
Sounds good, yeah. So if we take this red point right here, I may have drawn 3 collinear points, but I'll kind of squeeze the line so it doesn't look like that.
Don't have to be straight, so.
Yeah. So maybe we have something like this. Now in this bottom part, we have the same sort of problem, because we have the blue line and again a red point. We can draw this line safely, and now we've created 2 other triangles. The triangle on the left now has a red base with a blue far point. The triangle on the right has a red base again with another blue top point. So we can keep recursively solving this problem. Now eventually we'll run into the case, maybe we have it right here actually, in this triangle that I'm drawing in green, where there aren't any red points. So we can't recursively find whichever some point that matches the top. We can't find that and then connect it to the top point. But instead it's like pretty clear what we can do here, which is, since it's blue, we can just connect all of the blue points to this leftmost point.
So I think recursively some function gets 3 points being vertices of a triangle and some vector of points inside. And if possible, if there are 2 blue points and 1 red in a triangle, if 2 blue and 1 red, then we are looking for any red point inside. If we don't find any, and the problem becomes easy, because we just have only red points to connect to one. Two red points in a triangle.
So I'll just finish this one up really quickly. It'll look something like this. And that will divide this up again. And then if you can imagine just ignoring all of the white lines that I've drawn here, if you only look at the red and the blue, in this case we've successfully connected all of the blue points together and connected all of the red points together. We've done so in such a way that no 2 lines cross, because basically we've triangulated this in a useful way.
And some segments are even straight, so that's also a good thing to have.
Yeah, very cool.
Some of your triples of points are kind of collinear.
Yeah. I don't know, like, this solution might be possible if you have collinear points. If it is, it's a lot harder to implement, because you get weird cases for sure.
I think it won't be pleasant to discuss that and to think if we didn't miss anything.
Yeah.
No. Nothing is collinear.
Yeah, for sure. So that's a solution idea. There are a couple of things we might want to talk about here. The first is, what is the runtime of this? How fast does it end up being? So we have n points ends up to 10 to the 5th. In the data for this actual problem, the points were pretty much just random, and they were also just in a random order. So there weren't adversarial test cases against most solutions. So pretty much anything that you wrote, because it's random, would probably pass. But let's imagine for a minute this was like on a Codeforces set, and you had people trying to hack you. If you write anything that worst case is very bad, then it'll get hacked. So how do we find a way to like pass this if it were a Codeforces problem, maybe?
First, without we improve it in any way, it just n square, right? Because possibly n times we go into smaller recursive case.
Yeah, so worst case, you might have some triangle that looks like this, and then you might pick some point like this, and you might have an empty triangle over here, another empty triangle, and then basically all n of your points in this big triangle here. So n times, you do an order n sweep. For each of these points, you can just naively check which triangle are they in, and that just takes like some cross product checks. So there's no special data structure going on here to use the fact that it's Euclidean or whatever. You just like naively check it. But yeah, so you keep doing this. Worst case, you order n times, you do an order n for loop. So I guess I shouldn't circle that. So then the runtime would be order n squared.
I agree.
So maybe how might we do a little bit better? I guess do you have any ideas, Camille, on like approaches you might want to use immediately?
If somebody says that if the data is random, then we are fine. And the first idea everybody should have is let's make the data random, or let's try to do something in a random way. And I think it will work fine if we choose a random point inside. If we are able to choose a random point of proper color inside the triangle, and then we expect the split into 3 smaller triangles to be kind of even. Actually, it's not that all 3 triangles should have similar sizes, just that at least 2 of them should. As long as that's true, we're fine.
Absolutely, yeah, that's pretty much exactly the intended. So like one way of justifying that to yourself is this is basically like a 2D version of quicksort. So in quicksort, what you do is you pick a random pivot in some array, and then on average the pivot's probably not going to be perfect. It probably won't be exactly in the middle, but it's going to be close to maybe like 1/3 of the way through. And you'll split the array into about like 1/3 and 2/3 maybe. A similar thing happens in 2 dimensions, where you're going to split this up into some proportion. The exact math isn't too important, but basically you're splitting up the triangle into some parts, each have like some fixed constant size, which means in a logarithmic number of steps, you'll wind up having triangles that are about size 1 if you choose randomly. There is a deterministic solution as well. I don't think it's too important to go over, but basically it uses a similar idea to KD trees, if you're familiar with them. So you can like split up all of you can look at the x's for the first layer, then the y's for the next layer, and you can very quickly, like in some constant times log number of steps.
Something like first vertical split, then horizontal, then vertical, then horizontal, that thing?
Yeah, it's similar to that. So first you pick like the horizontally middle point for the first layer. Next time you pick the vertically middle point.
Can you show me any intuition why that works?
So I don't think it's kind of like a lot of pictures, and it takes a lot of steps, but
okay, if it's really complicated, then I think we can skip it, and just if we find one, we will provide a link maybe in the description to any longer explanation.
Sure. Yeah, it sounds like a good idea. Okay, awesome. So just one more thing left to talk about here, and that is how do we do this in the general case? So in this case, we started with just a square with some points of 2 colors inside of it. What if instead of it being a square, what if we just had a bunch of points? They could be anywhere, not necessarily in a square. How do we solve it then? So I'll draw some points here, maybe as some example of some problem we might want to solve.
And this more general version appeared a few times in different competitions, at least in Bubble Cup 2019, in some Open Cup competition, and maybe in 1 or 2 more places. A lot of problem setters independently come up with this problem. Maybe not independently, I don't know.
Here's kind of a very complex example. I'm gonna draw a simpler version of this, but we'll actually see that this turns out to be impossible. And it's maybe it's not super obvious immediately why. It seems kind of hard to do, but it seems like, well, maybe there's some way you can wiggle around. And here's like a simpler version, which is pretty clearly impossible. That one looks like this.
Four points are enough.
So if we have this, the red connection line has to look like this, right? If the red line looks like this, yep. Well, we can't actually connect these blue points because they'll be intersecting. So this is very clearly impossible. And if we look at just some subset of these red points, we can find something that looks like that. But that's not necessarily true, because if you add in more points, that gives you more degrees of freedom, so it might be easier all of a sudden. So initially, Camille, you mentioned that for the first problem, you looked at some convex hull ideas.
Yes, because I know that here, the first check we should do is find the convex hull of points. And indeed, from this idea about getting two opposite red points and two opposite blue points, we can get something interesting, because we can here try to see, can I choose a pair of red points far away from each other, kind of, and blue points such that their segments would intersect. And it's important that they are on convex hull, because they cannot now move outside of this. There must be something. That's the basic thing with planarity. If you want to connect those marked red points on left and right, you cannot connect blue points in bottom and top, even if those aren't straight lines. If we only can draw inside a convex hull, exactly, even like that, because maybe there are a lot of red points, now we cannot go from blue to blue without crossing that. There will be at least one intersection.
Exactly, yeah. So basically, just to summarize, what that kind of tells us is all of the red points need to form a continuous range on this circle. And similarly, if all the red points are in a continuous range, that means the blue points are either the rest of the range, or there aren't any blue points on the convex hull. So either all of the convex hull needs to be red, or you need to have like some, I'm going to say half of it, it might not be half, it might be like 90% of it, but you need to have some continuous range that's red, and then the rest needs to be blue. Let's look at a simpler example then. Maybe let's just fix this one so that it follows that rule. Well, I guess the easiest way would just be make this blue. So in this case, now we have exactly what we were asking for. And the follow-up question is, well, this isn't obviously impossible. Does that mean it's possible? Is there still some way of solving it?
I think that just like with the first problem, the proof is basically showing a solution that will always work. Or is there some other explanation without coming up with a solution?
I think constructive is probably the best way of looking at it. So similarly, what we did in the first problem when we had our square is we connected the two top points, and then we also connected the two bottom points. It's easy to think about this as, okay, this is the half of the convex hull that's one color, and then we also have the other half that's this other color. So we could do that. Let's try and do that initially up here. So we'll connect these 2 points right here. These will both be blue. And then we'll connect all of these points as red points. Now we have these 2 sections. Now, we already know, since there are no 3 collinear points, if we can split it up into the triangles of that earlier form, then we can keep things connected like we wanted them to.
Okay, but do we again draw the diagonal? One diagonal? Or...
one way of
just
doing
do
it,
triangulation. Okay.
Yeah, you can do any triangulation, really. So you can connect all of the points to this point here, and then you connect all of them to this one. It's one way of doing it. So here we just have 1, 2, 3, 4, 5 different triangles. All of them are the same, and we can do the exact same algorithm we used last time, except this time is, I guess, just more complicated.
My friends all often make fun of me that I have a weak memory, problems, for solutions. Even here, when you gave me this joining points problem from IOI, it looked familiar, but I didn't remember if I already solved it. But yes, I did, like 2 years ago. I mean, the general version in some training ICPC. But here, again, I didn't remember a solution, so I'm surprised how cool it is, how nice it is, even though I already knew it.
Sure,
it's a good thing about weak memory. You can relieve some problems.
Enjoy it for the second time. So I guess let's just talk about the runtime here, and then we should be good. So I guess naively, if we did the same approach as last time, we might have order n different triangles here, and we have to associate each one of these points with the triangle that they're in. So we have n different triangles, and each check takes order 1, but we have to check order n different points. And then we have a divide and conquer on top of that, which takes an extra log factor worst case. So we'll just say the runtime is about order n squared log n. It might be a little bit better than that, but that's, or I guess it's n squared plus log n, right? Because the second part is n log n.
Oh, right, yes.
So then the final runtime will just be order n squared. So we've got our runtime, we've got the n squared part to initially find which triangle is each point in. On top of that, we have the n log n, just the same as last problem. If we can improve this, then we can get our runtime down to n log n, so that's what we're going to try and do here. So what did you say, Camille? What were you saying? Do something like this, maybe?
Just dashed segments from one point, and for every point inside this convex hull, for every, those maybe they should be with colors. For every red point, we need to find out in which part of the drawing it is, between which two dashed segments.
Sounds like there's probably a good way of doing that in log time.
Yes, there are at least 2 ways I can think of. If you see one of them, I will then say the other.
Sure, so I think I see 2 of them maybe, but let me know. So the first is, we can order the triangles like this. If we do that, we can binary search which triangle we're on, and we can evaluate whether we should go higher or lower by saying, is it above or below this line? We know that's safe because we know this point's on the convex hull.
So even instead of thinking about that as triangles, we can think about it as the order of the n-1 points on the convex hull. Every point other than the first one. Exactly. This 0, 1 up to some n or n-1 too. And we can, when you have any red point, on this sequence of blue points, you can binary search and check if you are on the left or right from the blue point. This way, in particular, we could try to find, I wanted to say the closest point, but that's not true. The angle-wise closest 2 points. So this kind of binary search, and this is obviously the number of red points times logarithm of blue points.
Very cool, yeah.
In total, we have n points, so whatever. It's n log n.
Yeah. Another way that maybe is possible is we could do a sweep if we sorted both of them radially around this.
Yeah.
And then
this is, I think, what I would do.
Very similar.
Or just we can sort red points. If we already have convex hull of blue, then we know the order of that, and it's just sorting red and then doing 2 pointers.
Yeah, very cool. So I won't go into that too much, but basically the problem we're solving is pretty much that same version, except we want to do it on this corner here and then also on this corner here. Since we're connecting everything to one of the 2 corners, if we're able to do that, then we can pretty easily say which triangle it should be in. And then beforehand, we can just divide all of the points into 2 sections based on which side of this line they lay on. Awesome. Well, yeah, so that's the connecting points. I'll leave links to the 2 different problems that we discussed in the description if you want to upsolve them. And I want to thank Errichto for joining this one.
Thank you for having me. And my last remark will be that today I found how similar this is to Delaunay triangulation. And you viewers can read more about it. It's something complicated, so it's for sure not the topic for this video. But there, the first step is also to find triangulation of given set of endpoints. And the easiest method to do that is to keep taking the random point and doing the triangulation. And thanks to that, we have some good starting position to then run some improving. The total thing is n square anyway, but this first step is thanks to that very fast. I wasn't aware of that before today, that two problems are similar.
So yeah, anyway, thank you for joining. Make sure to check out the other video that we're gonna go do very soon. I don't know exactly when these will be released, but that'll be on Errichto's channel. So make sure you check that out, and hopefully you'll enjoy that one as well. Thanks everybody for watching, and I guess if you have any last words, you can do the outro, Camille.
What do you say after good morning? Goodbye? I don't know.
All right, yeah, sure. Goodbye.
Good night. Oh, yeah, good. I think good night has a lot of sense now. So good night, everybody. Bye-bye.